So in this, to start us off in our quadratics unit, I'm going to teach you guys or reteach you how to graph a quadratic from vertex form, and then we'll take a look at a form that some people call intercept form. Okay, so just to review, a quadratic is a y equals x squared graph. It makes a parabola shape, quadratic shape. Okay, so that's our parent function. And then we can transform that parent function in a variety of ways. We've already looked at the transformations that can occur on a function. So this really shouldn't be super unfamiliar for you. But what the piece that we're kind of connecting here is the idea that in a parabola, in the parent function, that vertex is at the origin. So when I cause shifting, which this plus number at the end of the equation and this minus or plus that happens with the x, those are shifting values, right? This h number would shift it sideways because it's with the x, and this k number would shift it up and down because it's away from the x. You remember that from when we graphed our absolute value graphs? Okay, but these are shifting the graph, but since the vertex is at the origin, that means these values are actually relocating the vertex. These tell you where the vertex lands. They're shifting all of the points in that same direction, but since the vertex was at 0, 0, whatever these numbers are, h and k, those tell us where the vertex is. So when we call this vertex form, we mean the vertex is readily apparent in the equation. Or like the SAT's way of saying that would be the vertex appears as a constant or a coefficient in the equation, which is true here. The vertex values appear as constants, numbers, in the equation. Okay, that's why it's called vertex form. So h and k are the vertex. They are the vertex. And so when you're pulling those numbers out of the equation and identifying the vertex, remember the h value changes signs, right? The sideways shift always goes against its sign. We're familiar with that, and that's true here. Okay, a is still your vertical stretch or compression factor, and remember your stretch and compression factors are if they're between 0 and 1, that's causing a compression. If that factor is greater than 1, that's causing a stretch. Okay, and then also that a value right there tells you if there's a reflection across the x-axis, a vertical reflection. Okay. And then this last little bit is helpful to remember. A vertical parabola, like an up and down parabola, is always centered about its axis of symmetry. Remember, the axis of symmetry is the line that goes down the middle of the parabola, kind of cuts it in half. It's symmetric on either side of that. Okay, and that's always centered about its axis of symmetry, which is x equals h. The h number, the x value of the vertex, is your axis of symmetry for a vertical parabola. Now here in a couple of days, we'll get into sideways parabolas and how to graph sideways parabolas. And their axis of symmetry goes sideways. And so their axis of symmetry would be the y value of the vertex. But that's not for a couple of days. Okay. So let's look at how to graph this. I'm going to show you, well, no, I'll show you that on number 2. So on number 1, all of my graphing strategies for this year will all really involve the same process. First, we're going to recall the parent function coordinates or table. Okay. For every parent function when I can, I use small whole numbers that are close to the origin, -2 through 2, because those are the most likely ones to show up on the graph. If you plug in 100, it's probably not going to be on the graph, or even 8. It's probably not going to be on the graph. So, and then in this parent function, we are squaring the x values. It's x squared. So square those x values. What do you get? What's 0 squared? 0. 1 squared is 1. 2 squared? 4. Sorry, -1 squared? +1. Remember, that negative times negative makes a positive. When you square a negative, it turns positive. And -2 squared is 4. Okay. So those are our parent function values. And then this has a shift occurring, the 4 and the 3. Which direction does the +4 shift it? Left. Yeah, this is left 4, and then the +3 is what? Up 3. So if you remember from our absolute value graphing, I like to artificially move the origin. So I kind of pretend to move the origin left 4 and up 3, right there. And then I graph my table from that spot, pretending like that little green cross is the origin. So from that spot, 0, 0, 1, 1. All right, and then from that pretend origin, it's 2, 4. So over 2, up 4. And then on the left side, over 1, up 1, over 2, up 4, because 1 squared is 1 and 2 squared is 4. Okay, so that's our parabola. Hey, just a point of clarity. What is technically happening is that each one of these points lands in their normal spot, centered at the origin, and then they all together are being moved left 4 and up 3. Okay? So I know that the way I graph it, I move the origin, but if you were to put it in a calculator and put the calculator in super slow motion, all the points would move together. The calculator would not move the origin over, it would move all the points over. Okay. So that's just important. I just know of SAT questions that hinge on that concept, you understanding that all the points move together. The origin doesn't move, the points move. Okay, so let's jot down some key information here. The vertex of this parabola is -4, 3. And the axis of symmetry, well, that's going right down the middle. It's a little, I'll do it as a dotted red line there. That is x equals -4. It's always, for a vertical parabola, it's the x value of the vertex. Our domain, oh, by the way, don't forget to actually draw the line for your graph with arrows, okay?
Do we have to draw the axis of symmetry?
Yeah. Yeah, go ahead and draw the axis of symmetry on these. Your domain is -infinity to infinity. From this point forward, most of our material will prefer interval notation. And when you get into pre-cal, pre-cal prefers interval notation as well. So you should just get used to giving that. Set notation is still fair game for the midterm and the final, but you're going to see me using interval notation. Okay? Range is bottom to top, so 3, infinity. Bracket or parentheses on 3? Bracket. Because it actually does hit 3. There's a real dot there. It came from our table. It's a solid dot. Okay? And then there is one more category that we often ask you about, min/max, and then the value of that min-max. So we'll start with min-max first. Is there a minimum or a maximum on this graph? It's a min. What does min mean? What is that short for? Minimum. And what is that? Yeah, in your own words, that's the lowest point on the graph. So this point it bottoms out right here. How low does it go?
3.
Yeah, it goes as low as 3. So first of all, you need to circle min or max. It is a min. And then you need to say how low it goes. It goes as low as 3. Or you could write -4. You could write the coordinate as well. Okay. You could write it either way. When you get to pre-cal, they probably will start doing the coordinates. Okay. But I see a lot of Algebra 2 teachers just do the y value, and I'm okay with that. Okay. So that is how we graph a vertex form. Notice I got to use just the table as it was here. Tell me a scenario where I have to make an adjustment in the table. If we have a stretch or compression, like a multiplier here, I have to multiply that into the table wherever it belongs. So taking a look at number 2, we have that case. But even before we start graphing, I want you to start being able to identify key pieces of information. So right away, you can tell that your vertex is 2, -5 because of the vertex form. This is the x value of the vertex. This is the y value of the vertex. We always switch that x value sign because things that are with the x always go backwards. Great. And since our vertex is 2, the x value is 2, we can automatically know that the axis of symmetry is x equals 2. So just go ahead and write those. You know those even before you graph it. You shouldn't have to graph it to know those. And then the domain. Yeah, our domain is negative infinity to infinity because all vertical parabolas do this. Whether they're opening up or down, they have this domain. Okay, and let's go ahead and even determine min, max. So like right away, because we see that positive a value in the front, we know that this is opening up and therefore has a min. Okay, and what is its min value? How low is it going to go? -5. The y value of the vertex is on a vertical parabola is going to be that minimum or maximum. Okay, so a lot of these we can tell right away what they are. Now the range, you could even fill in the range, but I'm going to go ahead and graph it before I do that part, okay? So let's recall our parent function tables, -2 through 2, square those x values. So 1 squared is 1, 2 squared is 4. When you square a negative, it turns positive. Okay. And then, so we talked on the last question about like the order of transformations. Like what would happen first? What is the proper way to transform these equations or these dots? So I mentioned that the shifting would be last, and all of the dots would shift together. But the first thing that would happen here, these are my normal dots. You don't have to graph this. You can just wait. These would be my normal dots. The first thing that would happen to them is that the y values are getting multiplied by 2, okay? You know, that 2 in the front of our equation, that is a vertical stretch or compression, and it multiplies the y values. Why does it multiply the y values? How do I know that it doesn't mess with the x values? Because it's not with the x. It's not in parentheses with the x, okay? So it's multiplying the y values. But conceptually, here's what's happening. It is multiplying each one of these dots' y values by 2. So 4 is getting doubled up to 8. And 1 is getting doubled up to 2. And 0 is getting doubled and staying at 0. Okay, so all these 1s bump to 2, the 4s bump to 8. Okay, and then all of those new dots, the purple dots, they're getting shifted according to the shift. So a stretch or a reflection happens first, and then the shift happens. And you know, we already jotted down the vertex, but the shift, of course, is right 2 and down 5. Okay, so all of these are moving right 2 and down 5 together. Now, like we talked about in the last one, I like to move the origin right 2 down 5. You know, I pretend like the origin is down there and I graph my table from there. But if you want to skip the table on an easy one like this, I'm okay with that. And when you get to pre-cal, you know, when your pre-cal teachers start graphing sine and cosine waves, they might skip the table and just double the height of all the dots because they know that's what the 2 does. Okay. So 0, 0. 1, 2, -1, 2, 2, 4, -2, 4. Don't forget your arrows. And then, what is the range now? Somebody give me the range. So our range is -5 infinity, right? Bottom, comma, top. It bottoms out at -5. Okay. If you're good with this one, why don't you try number 3? Try number 3. So here's number 3. Give it a shot. And if you need a hint, look up here for a hint. You probably want to put it in this form first. Okay. And the first step to doing that, if you need another hint, the second hint, look up here. If you need that hint, that's my first step into getting it into that form. And here's how I write that first step. Okay. So try this one on your own. See if you can get it into the right form from here. If you need a third hint, you can look up here. There's my third hint. Which gets it into vertex form. Yeah, so someone just asked, when you divide by this -2, why are these things being divided by -2? Well, I would say they are. It's just not being done yet. Instead of actually applying the division, well, first of all, I couldn't apply the division because I would have to apply the squared first. PEMDAS says that exponents has to come before multiplying and dividing. Okay? So, and I don't want to FOIL that. I like vertex form. It's helpful to have it in vertex form. So I don't want to apply the squared. So instead, I'm going to slide that divide by 2 off to the side as a -1/2 multiplier. So I can maintain vertex form. Because vertex form is nice. We can tell what the vertex is. Okay, so now you've got that form. Why don't you see if you can finish out the whole graph and fill out all that information. Check your answer up here when you're done. All right, as you finish up your graph, check yours up here and check that information. I'll kind of walk around and answer questions if you've got them. Okay. Number 4 and 5 and 6 have us using equations and exploring the relationship between equations and transformations. So number 4 is nice and easy. Describe the transformation from the parent function y equals, or g of x equals x squared. So somebody just shout out, give me one transformation that you see. Vertical stretch of, okay, so vertical stretch by a factor of 7. Okay, and that's why we know it's a stretch and not a compression. Stretches have a factor over 1, compressions have a factor between 0 and 1. Cool, what else? Somebody new, give me a new one.
Horizontal shift left 1.
Yeah, a horizontal shift left 1. Okay, that plus 1 with the x is sideways, and it goes against its sign, so it's going to the left. And then how about one more? Yeah, thank you. Down 5, down 5. Cool. That one's nice because it's just from the parent function. Look at number 5, though. I accidentally typed the word parent function, but really this isn't the parent function. We're starting with something other than the parent function. So I want to know what the transformations of f of x are if it started out as h of x. So first of all, let's look at the vertical shift. We started out at a +4 and it moved down to a -2. Yeah, it was up here. It was up there and it moved down. It ended up down here. That means it went down 6 units. Okay, so our transformation is not down 2, it's down 6 because it started up at 4. It didn't start at 0, it started at 4. So, and then the horizontal shift is started at right 1, and then it went to the left 5. So if it started at the right of 1 and it went all the way to the left of 5, that means it went 6 units over to get to the left 5. So left 6. And then our vertical stretch factor, it started out as a stretch of 2. And then it ended up as a vertical stretch of 4. So how much more stretching did it have? Like what factor had to be applied to the existing stretch to turn into a stretch of 4? 2. Vertical stretch by 2. Okay. So it's not comparing it to, the parent function has a stretch factor of 1. So it's not comparing it to, what'd you have to do to that to turn it into a stretch of 7. It's what additional multiplier was necessary to get from a 2 to a 4. You needed another multiplier of 2. Okay, hey, see if you can write the equation for number 6, and then we'll move on to that last page. So, number 6, I give you the transformations. See if you can write the equation. check your answer up here as you finish up. I tried to color code my function so that you know where each one of those pieces came from. I am missing one small detail, so see if you can find it. Don't shout it out. See if you can find it. I'll reveal it in a sec. Yeah, I left off the squared on accident. Ugh, annoying. There's a squared there. Don't forget that. Okay. You notice that I used a instead of x, and that's because that's the input they gave me. They call it f of a, so they want me to use a as the input, so I used a instead of x. Okay. Yeah, so the question was asked about the reflection. So if I have something that's reflecting across the x-axis, that is a vertical reflection. So don't get deceived by the fact that the x-axis is a horizontal axis. If it's reflecting across it, it's an up and down reflection, vertical, so it belongs outside of the parentheses. Okay. All right, moving on to more skills you've seen before but maybe have forgotten. In this lesson, we are writing the vertex form of a quadratic. Writing the vertex form from a vertex and a point that it passes through. Okay, so remember, vertex form is, you've got to know it. It's y equals a times x minus h squared plus k. And in these kind of problems, I'll give you the vertex, or I'll give you enough information to know the vertex. Okay, so here on number 7, sorry, the numbering is a little wonky on this page. We've got the h and the k. It's given to you in the form of the vertex right there. Okay, and then what are we using this extra point for? Does anybody remember from their Algebra 1 class? This extra point, or any point that the graph passes through, is going to be, this is a extra one-time use point. We are going to use it one time as x and y, only to find a. And once we find a, we're going to throw that extra point away. We will not box an answer that keeps the extra point. Okay? A quadratic equation has y and x in it. So your answer has to have y and x in it. Okay. We're just using these y and x numbers for a moment. So here's what that looks like. We have our y equals, so negative 15. Negative 15 equals a x, which is 1, minus
Isn't it plus? It's going up.
negative 2. And then we have the squared plus 3. Okay, that's everything plugged into vertex form. And there are a couple of things that jump out at you right away, like minus negative is a plus. Okay, so I can come in here and really clean it up pretty quickly. Negative 15 equals a 1 minus negative turns into plus. So that's 3 squared plus 3. What is 3 squared? 9. So this is a times 9, negative 15. And here's the mistake everybody makes on this problem. Everybody wants to add 9 plus 3. Can you add 9 plus 3? No. Why not? They're not like terms. This is not 9. This is 9a. This is a times 9. This is 9a. Okay? That's why it can't add to the 3. Nobody would add 2x plus 1 and say it's 3, because those are not like terms. So instead, subtract the 3 to the left side, makes it negative 18, and then divide by 9. So a equals negative 2. Okay? So here's our vertex form then. Y equals negative 2, I'm going back to y and x plus 2 minus negative 2 plus 2 squared plus 3. Don't forget your squared. So that's your vertex form. And then they also asked you to put it into standard form. Hey, see if you can do that on your own. Get it into standard form. We'll pause the video. There's your first step if you're stumped. When you square something, you are multiplying it to a copy of itself. So x plus 2 times another x plus 2. Don't call it x squared plus 4. That's not how it works. FOIL, or double distribute. X times x times 2, 2 times x, and then 2 times 2. Okay. Once you get done foiling, your next step is to distribute that a value out front, negative 2. Distribute that into your trinomial. And then you combine your like terms after you distribute the negative 2. Number 8, we'll hold off on number 8. If you want to see a completed version of number 8, you can check out the completed notes in Canvas. But there's your completed number 7. And then, again, apologies about the numbering, so we're going to continue on to number 4 from number 8. It's fine. Okay, so the last thing that we're covering today is intercept form. Intercept form is just a form of the quadratic equation that shows the intercepts. You know, and if you're using SAT terminology, they would say, you know, like, this is a form that shows the intercepts as a constant or a coefficient in the equation. It's a number that is seen in the equation. That number is the intercept. Okay, so when it's in factored form, these factors, see the parentheses there and parentheses. Okay, those factors tell us the intercepts. So it's x minus a number for each of them. So those numbers are the intercepts, p comma 0, q comma 0. So the x-intercepts of a quadratic have many names. They can also be called zeros, solutions, or roots. Okay. As a rule of thumb, when we call something a 0, that is usually written as x equals. When we call something an intercept, that is usually written as a coordinate x comma y. Okay, so just kind of how terminology is connected to the form of the answer. But you can use any of those terms interchangeably. Okay. To find x-intercepts in standard form, if it was given to you in standard form, which is this, like this form, we would have to factor it first, and we'll review factoring here in a couple of days. Okay. If factoring isn't possible, we'd have to use another strategy like complete the square or quadratic formula. We'll review those too. This is a big important one. The x value of the vertex, also known as the axis of symmetry for a vertical parabola, is the average of the two x-intercepts. It is right in between them. Okay? And then that last point, if there's only one x-intercept, well, then that's the vertex. And you think about that. If I have a parabola that's only touching the x-axis once, then that means the vertex is where it's touching. Okay? It's bouncing right off the x-axis. Okay, so let's graph these. So number 4, these really are pretty easy. You just take the factor and you set it equal to 0. So x minus 2 equals 0. X plus 4 equals 0. So x equals 2, x equals negative 4. So down here where it asks for the zeros, we could write that as x equals 2 and negative 4. You know, or you technically could write it as a coordinate. That would be fine. Negative 2 comma 0, negative 4 comma 0. Yeah, but the reason that sign changes technically, you really should think of it as you're setting the factors equal to 0 and solving. That is the fundamental reason why that sign is changing. Okay. So we've got our, go ahead and graph your x-intercepts. You've got one at 2 and negative 4. Okay, which means your axis of symmetry is right down the middle at negative 1. And you're like, well, how did you know that? Well, you could check by averaging averaging the two x-intercepts. Negative 4 plus 2, and then divided by 2 is 1. Negative 1, excuse me. So your axis of symmetry is negative 1, and then here we go. You ready for this? Which means your vertex is negative 1, comma something. Okay. The axis of symmetry shares the same x value as that vertex for a vertical parabola. Our sideways parabolas will be different. How do I find the y value of the vertex?
You have to factor it. No.
How do I find the other half of a point anytime I have the first half of a point?
Plug it in.
Plug it in. This is what you do anytime you have half a point. So I'm going to plug it in. So y equals 3 times negative 1 minus 2 times negative 1 plus 4. And I'll do the math. So y equals 3 times negative 3 times positive 3, which is negative 27. Okay. Hey, some people do this. Look up here. This is a silly mistake. Some people are like, oh, I got to distribute the 3, and they try to distribute it to both. That's not how distribution works. It only distributes to the parentheses next to it. It doesn't distribute into multiple sets of parentheses. Okay? Like if I gave you a question that was like, okay, 2 times 5 times 1, no, that's a bad example, times 3, wouldn't you just say, oh, okay, 2 times 5 is 10, and then times 3 is 30?
Yeah.
You wouldn't do 2 times both of these. Okay? But you would be surprised how many people try to do that. All right. Negative 27. So our vertex is not really going to show up on this graph. So we can sketch, and it's going to go off the grid somewhere. Back up, something like that. It goes way lower. Negative 27 is like actually way down here. Okay, but I don't want to mess up this graph, so we'll just stop it there. Okay, so what is the range? Yeah, the range is negative 27, bottom comma top, negative 27 comma infinity. Thank you. Okay, so that's how we graph intercept form, and those are some of the pieces we know about a graph from its intercept form. I didn't mention this, but this 3 right here, that is A. That is the same A value that you would multiply into a table if you wanted to. Okay, so if you came up with a table for this, you would multiply the y values by 3. It's the same A. Okay, why don't you try number 5 on your own? This will be our last one. I'll put the answer up here in a minute. It's a challenging one, so buckle up. So this is kind of me getting started. I took the factors, set them equal to 0, and then I got my x-intercepts, or my zeros, negative 1 and 6, okay? And then, the axis of symmetry is right in between them, which is kind of hard to tell because they're 7 apart from one another, so the math for that is averaging them. Add the 2 zeros together and divide by 2, negative 2.5, okay? That's my axis of symmetry, which means my vertex is negative 2.5, comma something, okay? And I also can tell right away from the equation whether this is a minimum or a maximum. I don't know if you realize that. I can look at the A value. I can see what is the sign of my A value. A is less than 0. It's a negative, which means that this is going to be an upside down graph, which will have a maximum. I don't yet know what the max is, but I know that right away. Yeah, quick correction there. Positive 2.5, because negative 1 plus 6 is positive 5. Thank you for that. Okay. So now I'll carry on with finding that y value of my vertex by plugging in the x value. So when I plug in 2.5, I've got some kind of yucky multiplying to do there. But it's doable. 3.5 times 3.5, you can do that off to the side. It's negative 12.25. And then the last thing, the y-intercept. How do I find the y-intercept? Well, I know that any y-intercept ever starts with 0, comma, something, because the y-intercept is where x is 0. So if I have half the point, well, I can plug in, find the other half. So I'll plug 0 in for x to find the y value of the y-intercept, which is 3. And that is how we graph from intercept form.